I'm going to be describing our system, differentiable ILP. It's a system, a neural network that learns logic programs, specifically data log programs, from examples. It learns those programs by back-propagation, so it's robust to noisy mislabeled data and also to ambiguous data. So this is coming out next month in JAIR, but you can read the paper now on arXiv. So I'm going to give a quick background. I'm going to describe our differentiable ILP system, and then I'm going to describe some of the experiments that we performed. So briefly, the overarching problem that we're trying to solve is learning programs from examples. So given some input-output examples, learn some sort of general procedure that turns the inputs into the outputs. So for example, if our inputs are lists and our outputs are integers, here we want to learn a procedure that returns the length of the list. Or if our inputs are lists of lists and our outputs are lists of lists, in this case, we want to learn a procedure that chops the last element off each of these lists. And we want to learn a general procedure that generalizes. So we give it a few examples, and it generalizes, a general procedure. So I'm going to describe various different approaches to this general problem, and then our specific way of doing it. So the first approach is symbolic program synthesis, the second is neural program induction, and then the third type of approach is neural program synthesis, of which our method is one example, as is Tim Rochechel's and other people's. Okay, so first I'm going to describe symbolic program synthesis. So here we're given some input-output examples, and we produce an explicit human-readable program from those examples. And in this class of approaches, we use some sort of symbolic search procedure to find the program. So perhaps we do best-first search or heuristic search, or we compile it into a SAT problem and throw it at a SAT solver. But the two crucial features of symbolic program synthesis are we're generating an explicit program that we can read, and we're using some sort of symbolic search procedure to find that program. So for example, given input-output examples like on the left, a symbolic program synthesis technique might output a Python program like this. So it outputs a human-readable program that satisfies the examples and generalizes to new examples. So notable examples of symbolic program synthesis techniques include magic Haskell, lambda squared, Igor, Progel, and Metagol. Now, these approaches have some very appealing features. Firstly, they're very data efficient. You can give them a handful of examples. You can give them 5 examples, and they can learn a program that generalizes. The thing that they spit out is an interpretable, human-readable program that you can verify. They tend to generalize well outside the training data they've been given. This is because we're searching over programs. Programs in general are general types of procedures, and we tend to be searching for short programs, and short programs tend to generalize well. So these are the good features of symbolic program synthesis. However, the two less appealing features is they're not always robust to mislabeled data. So with a lot of these symbolic program synthesis techniques, if you give them a single example of mislabeled data, they're unable to learn the desired target program. They're not robust to mislabeled data. There are a few examples of symbolic program synthesis techniques which do learn from noisy data. But in general, it doesn't come out of the box. You have to work hard to get them to achieve that. But perhaps more importantly, they're not robust to ambiguous data. What do I mean by ambiguous data? Well, imagine that you have a robot going around and it has a camera just looking at things. So its data is not crisp symbolic inputs. Its input is just raw pixels. So for example, it's given some sort of image of some sort of digit. It doesn't really know what it is. It has some probability distribution over what it could be, but it doesn't know for sure. So symbolic program synthesis techniques can't handle this kind of data, distributions over inputs. So the second type of approach is neural program induction. Here we have a neural network. We give it lots of input-output example pairs, and it learns a procedure, a general procedure. So now if we give it new inputs, it'll spit out new outputs. Here there's no explicit human-readable program. The procedure is merely implicit in the weights of the neural network. There have been a number of recent examples of this neural program induction approach. So the neural Turing machine, the differentiable neural computers from Alex Graves and others, the neural stacks and queues from Ed Greffenstedt and others, and related work from the Facebook group, the neural program interpreter from Scott Reed and others, and the neural GPUs. So these are all neural networks that turn inputs into outputs. So these have a very different class of characteristics. So in terms of their really appealing features, right, they're robust to mislabeled data. You can give them lots of noisy data, and they can still learn a nice general procedure. And they can handle ambiguous data. So these are their appealing properties. However, these are their slightly less appealing properties. Sorry. They're really not very data efficient. You need to often give them thousands of examples, tens of thousands of examples, hundreds of thousands of examples before they'll learn a general procedure. They're not interpretable, right? The thing that's learned is simply, it's just this massive tensor of floating point numbers. It's very hard to interpret what has been learned. And they don't always generalize well outside their training data. So for example, you train a neural network to add two numbers, and you give it numbers of length less than 10, and you give it lots and lots of examples. And then you give it, at test time, new examples of length 20. Most of these systems don't perform very well. OK, so the two types of approaches I've described so far are here and here. And they interestingly have sort of complementary properties. The things they're good at are the ones the other ones are not good at. And what we'd like in an ideal world is something that achieves all these requirements. And that's we claim neural program synthesis can achieve all of these 5 requirements. So here, we produce an explicit human-readable program, but we use some sort of optimization procedure, e.g. gradient descent, to find that program. And the idea is that this gets the best of both worlds. So examples of this are R-system differentiable ILP, robust fill, differentiable forth, and end-to-end differentiable proving, which Tim Rochester will be talking about right after this. Okay, so in terms of sort of our square of possible approaches, up here is whether the procedure is implicit in the weights or explicit human-readable program. And down here is whether we use a symbolic search or an optimization procedure. And the techniques I'm going to be talking about is here. And the aim is to satisfy all these requirements. OK, so our system, differentiable ILP, induces logic programs, specifically data log programs, by back-propagation. The way it works, it starts off with a language definition and some background axioms. We generate, from the language definition, a set of clauses, potential rules in our program. Then, using our axioms and our clauses, we infer some conclusions. We then compare our conclusions with our desired conclusions, take the cross-entropy loss. Because this system is differentiable, we can back-propagate through it, modifying our clause weights. Our clause weights here are how much we believe these various different rules should be in our program. That's the general approach. So in terms of the core data structure that the differentiable ILP system is operating on is evaluation. This is basically a probabilistic continual relaxation of a truth value assignment. So we have a set of ground atoms, including the always false atom. And a valuation represents how likely it is that these ground atoms are true. So it's a vector that's as long as there are ground atoms. The crucial idea is that at initialization time, not during training time, each clause that's been generated is compiled into a function from valuations to valuations. So for example, if we have the clause, this is a particularly simple example, if qx is true, then px, and this is our current valuation, i.e. we think it's slightly possible that qa is true and slightly more possible that qb is true. When we compile this clause into a function from valuations to valuations, it produces this result. It's more complicated for larger clauses that have multiple atoms in the body and when we've got existentially quantified variables, but these are technical details. The crucial idea is that we have these valuations, and each clause is compiled into a function from valuations to valuations. So this is basically one step of forward chaining inference using this particular clause. So then we have all these different clauses. This is a slight simplification of what we do, so it fits in easily. We have all these different clauses, and then we effectively take the weighted sum using softmax based on our weights. So we have these weights, which represent how probable it is that these clauses are part of our program, and we take the softmax, thereby combining together these different forward chaining inferences. And then, but we've also got we've got the facts that we already knew, which are the facts at time at. And we want to compute the facts that are true at the next step of forward chaining, so we combine them together using the probabilistic sum. But of course, forward chaining inference, which is what we're doing here, involves unrolling over a number of steps. So we effectively have an unrolled neural network over multiple steps to compute the consequences, and then the consequences of those consequences, and so on. So what I've been describing here, right, is this inference step. So this inference step is a differentiable implementation of forward chaining inference on data log clauses. And because it is differentiable, we can back-propagate the loss, thereby modifying our clause weights. So that's the central idea of our system. Okay, so some experiments using this as system. So first of all, we tried some standard ILP-style tasks from arithmetic, lists, and graph theory. I'll describe a couple of those examples. So one example, we're trying to work out the difference between cyclic and non-cyclic nodes. So a node is cyclic in green if you can get back to it, and it's in blue if it's not cyclic. So we give it a small number of training examples, like 3 different graphs, and we tell it which are the examples of nodes that are involved in cycles, and we tell it which nodes are not. So we tell it the difference between the green and the blue nodes. Then we want our differentiable ILP system to be able to learn what that difference is. And so here is the program it spits out. So it has to invent an invented predicate here, pred. So a node X is involved in a cycle, i.e. it's one of the green nodes, if it has this pred relation to itself. And then the pred relation here that's invented is recognizably the transitive closure of the edge relation, i.e. the connected relation. So what it's saying here is a node is a cyclic node, a node is a green node if it's connected to itself via some series of steps. So this involves the 2 crucial features of ILP, which are recursive predicates and predicate invention. So another example is Fizz-Buzz. So Joel Gruss wrote a very amusing blog post a couple of years ago about writing a computer program to play this game. I don't know if you know about this. The game of Fizz-Buzz is a simple children's game where we enumerate the integers, but whenever the integers divide by 3, we say fizz, and when they divide by 5, we say buzz. So Joel Gruss was invited apparently in this blog post, he was invited for a job interview, and the idea was that he would write a program that simply produced these Fizz-Buzz. However, as a kind of joke, instead of just directly coding this up in a few lines of Python, he did it as a machine learning exercise. So he trained a neural network to be given lots and lots of examples of this mapping, and then to generalize outside the training. So he actually trained it on numbers from 100 to 1,000 and holding out numbers from 1 to 100. And he used a standard multi-layer perceptron. And perhaps not very surprisingly, the neural networks totally failed to generalize outside the training data they were given. So even though eventually the training loss went completely down on the numbers it had been trained on the numbers that were held out, which was 1 to 100, it was no better than random. So it hadn't really learned the rules of Fizz-Buzz at all. It had simply, in some ways, memorized the data it got. And this is what John McCarthy calls that neural networks can suffer from the propositional fixation, i.e. they can effectively learn things which are more like propositional logic rules, but not first-order rules. What we'd really like is a neural system, right, that can actually learn this in its full generality, so it generalizes to any numbers. That's what we'd really like. So we threw this problem as our differentiable ILP system, and this is the program it learned for doing Fizz. So a number satisfies the Fizz predicate, right, if it's divisible by 3. So what it's saying here is it's a Fizz number if it's 0, or x is a Fizz number if there's some other number y which is a Fizz number which satisfies the pred1 relation, which is an invented predicate. And the pred1 relation between x and y is true if x is 3 smaller than y. So it's correctly learned a recursive understanding of this Fizz relation that generalizes to any numbers. Now, the really nice thing about ILP methods in general is they can implement a form of continual learning. So you've learned a program from one problem, and then the sub-programs that you've learned can be copy and pasted and used in other programs. So we can accumulate knowledge over time and use it to solve other problems. And this is an example of continual learning right here. So the two auxiliary predicates which we invented to solve this task are the x is smaller than y by 2 predicate and the x is smaller than y by 3 predicate. And we will use these in the next task. So the next task is learning Buzz. So Buzz is the property of being divisible by 5. And this is the program that the differentiable ILP generates. So a number that satisfies Buzz if it's 0, or if there's some other number that satisfies Buzz that's related by this predicate 3 relation. And the predicate 3 relation is true of x and y if x is 5 smaller than y. And it's generated 5 smaller than y by combining together the being 2 smaller and the 3 smaller. So it's used the learning it got from the previous task to bootstrap for this task. So the nice thing about this technique is it generalizes to any numbers. So the program that it's learned is a truly general program which works on any numbers, unlike some of these standard multi-layer perceptrons which don't generalize so well outside their training data. Right, so that was standard symbolic tasks, and now we're going to talk about mislabeled tasks. So these are tasks where we give it a certain proportion of mislabeled data deliberately. We willfully and naughtily mislabel some of our training examples. Now, many symbolic program synthesis techniques fail entirely if you give them any mislabeled data. They just cannot work in this case. So we tested differentiable ILP with different proportions of mislabeled data. So rho here is the proportion of training examples which are willfully mislabeled. So here on the x-axis is the proportion of examples which are willfully mislabeled. And on the y-axis is mean squared error, so smaller is better, lower is better. The thing I want to draw your attention to is the fact that if we give it a certain proportion of mislabeled training examples, up to 20% of mislabeled examples, it gets a good answer. So it's a nice, robust system that learns these interpretable declarative rules even in the face of mislabeled training data. Perhaps more importantly than mislabeled training data is learning from ambiguous data. So supposing you've got some robot going around and it has a camera and it just has raw pixels. We would like, if those raw pixels are going to be fed into any sort of system like this, we're going to have to be able to handle ambiguous data. So the example we use to test this is learning the less than relation on numbers, which is like a symbolic conceptual type of task, but from raw pixels. So in this task, we're given a pair of raw images, MNIST images, and we're given a label indicating whether the left image represents a number that's less than the right image. We give it lots of examples like this, and we want it to learn the less than relation. So this is combining, if you like, perceptual information and conceptual. It has to do perceptual learning and conceptual learning. We're going to test this on two types of generalization, what we call image generalization and symbolic generalization. So image generalization is what neural networks are really good at. So if you've given it lots of examples of images of 2 and 4, and we've told it that 2 is less than 4, then if we give it a new pair of images for 2 and 4, but new images it hasn't seen before, but it's seen the idea that 2 is less than 4 before, then neural networks are good at making this sort of image generalization. So that's the first type of generalization we wanted to test. But the second type of generalization we want to test is symbolic generalization. So here, we've given it examples that 2 is less than 3 and that 3 is less than 4, but we haven't given it any examples at training time of 2 being less than 4. And now at test time, we want to see if it infers that 2 is less than 4. Symbolic generalization. Neural networks are not good at this. Not out of the box. Not standard MLPs. So here are all the different pairs of digits and the different less than relations between them. And you can imagine that we progressively hold out more and more of these pairs. So we give it no examples of 1 being less than 6. So we hold them out. Now, you or I, we can infer, from all the examples we can see, this looks like a transitive relation. But neural networks don't tend to, out of the box, make that sort of inference. Okay, so this is our task. We're trying to learn the less than relation on images. And we're trying to test it on these two different types of generalization. So we created a standard multi-layer perceptron baseline to solve this task. So here we have a convnet. We get the output of the convnet is 2 vectors of length 10. We concatenate them together to get our vector. We then have a single hidden layer, and it's fully connected. And then we're just trying to minimize cross-entropy loss. So this is a very standard multi-layer perceptron. Now, if we give it every single one of those pairs of digits, then the MLP baseline can solve this task well. However, as we start to progressively hide certain examples from it, it does less and less well. Whereas our architecture does not have this property. So in our differentiable ILP, when we were feeding it symbolic inputs, we just had these axioms here. We just made a single change to our architecture so that it works coming from images. So we replace this little bit here with this little bit here. This is just a standard convolutional net that's given the image and creates some sort of distribution over how likely it thinks that the image is a 1 or a 2 or a 3 or a 4, whatever. Yes, we convert the logits into a probability distribution. So now our model is able to solve this task. This is the program that it learns. It says, this is a true example of a less than if x is my right image and y is my left image, and this pred2 relation holds between y and x. And this predicate2 relation, which is invented, is the less than relation. So this is learning a declarative interpretable program from these images. Right, so this is comparing our multi-layer perceptual neural network baseline with our differentiable ILP system. On the x-axis now is the proportion of pairs of digits that have been held out during this training. Pairs, so it's never seen, down here it's never seen 40% of the pairs of digits at all. But so you notice that the standard neural network degrades. The more and more pairs of digits it holds out, it has no way, if it knows that 2 is less than 3 and that 3 is less than 4, it has no real way of inferring that 2 is less than 4. This is the propositional fixation of neural networks. Whereas, by contrast, our system, even if it's only seen 40% of the data, is able to generalize. This is because it has an inductive bias towards recursive programs in general and things like transitive closure in particular. So to summarize, this system aims to combine the advantages of symbolic program synthesis with the advantages of neural program induction, to have low sample complexity, to learn interpretable rules that are robust to mislabeled data and can handle ambiguous data. The idea is this could be plugged into an agent that starts from raw pixels. And I'd just like to mention that if there are other people here who are interested in working on the intersection of logic and neural networks, we'd love to hear from you. So please talk to Ed Greffenstedt or myself anytime. Thank you. Thank you.